Okay, so our final speaker for the session and also one of the main organizers of this conference is Georg Gottwald. He is a professor at the Department of Mathematics and Statistics at the University of Sydney, and he will be talking to us about the validity and failure of linear response theory. So thanks, Georg.
Thank you very much, Cecilia. Thanks, Gary, and thanks, Peter. So this is joint work with Caroline Wormel, and we'll be talking about linear response theory and a particular aspect of it. So linear response theory, if a dynamical system has linear response, then it allows us to study the effect of small perturbations to average quantities by using only the knowledge, the current statistics of the current unperturbed state. So it's a very powerful tool, has been used successfully in statistical mechanics. And this talk is concerned with the following conundrum. So linear response theory has been widely used outside of equilibrium statistical mechanics in the climate sciences with fairly good results, and it has been quite a success story to study influence of sea surface temperature anomalies and things like that. However, mathematicians found recently that typical low-dimensional systems, so very simple systems like the logistic map, they do not obey linear response theory. So the question we're addressing here is, if we view a high-dimensional system, such as the climate system, as composed of lots of smaller, coupled small dynamical systems, how can we get an overall linear response if the individual microscopic constituents do not obey linear response? So that's the general question we are concerned with here. I'll make all this a bit give much more detail what's happening here. I have to put this bar away. Just a very brief slide on linear response theory. So let's say we have a dynamical system here, and it supports unique invariant physical measure, and we're interested in average quantities of this measure of some observable psi, and epsilon is a parameter that allows us to study perturbations. And then we would like to know, once we perturb the parameter epsilon from some epsilon 0, what is the expected value of this observable. And linear response theory, if valid, allows you to write it in this form, in this linear form here. This is now linear in the perturbation. And the expectation value of here is taken with respect to the unperturbed system, to the measure of the unperturbed system. So the only knowledge we have to have about the system is the current knowledge, and it allows us to say something about the perturbed state. Here again, the formula for linear response theory. So sufficient condition is, you can think of this as a Taylor series here, that the invariant measure is differentiable with respect to epsilon. So we can do a Taylor expansion of the invariant measure here. And just to show you this sort of the smoothness, what the smoothness of this invariant measure means with respect to epsilon, think of an Ornstein-Uhlenbeck process here. So this is the invariant measure. And now let's perturb a little bit the gamma here, that damping parameter. Then you see that the here in the shaded in this opaque curve is the unperturbed invariant density. So it smoothly deforms. Okay, so this is when linear response theory is valid. That's what we like. So now a couple of slides on success stories. First, let's start with success stories in the climate sciences. So when we go outside of equilibrium statistical mechanics. So it all started with Lees in 1975, and since then it has been applied to toy models, so barotropic models, quasi-geostrophic models, but also big atmospheric models and coupled climate models with fairly good success. However, there are examples in the climate sciences of models that show a sensitive dependency towards changing the parameters. And so problems have been known, and even if linear response is valid, then the fluctuation dissipation theorem might not be. So there's a work by Cooper and Heinz. And moreover, so this is a sort of little side avenue I'm going to take in this talk here, going away from solving this issue of the conundrum. Even if linear response is not valid, so if we know that the system is not valid, it might not be detectable for us in a finite time series. So I want to say a few words about this. So if you're a practitioner, you're given a time series of finite lengths, and you want to test for is linear response valid or not. And what you find is in order to detect linear response, you might need a very, very long time series. So this is for logistic maps, a very, very simple system. Here a bar is the average of the observable. So this is a response. Here is epsilon, the parameter that we change from the unperturbed epsilon equal to 0. Here are error bars shown, and given those error bars, if we have 100,000 times of 100,000 points in our time series, then we cannot, we can accept the null hypothesis that this is respecting linear response. However, we know the logistic map, I told you that it does not obey linear response. Only when you go up to 1 million, you can see that linear response is not consistent with the observations here. So the detectability of a failure of linear response or of linear response depends on the data size, as we've seen here, on the size of the perturbation, because if the perturbation size is very small, it's hard to distinguish it from the sampling effects of your finite time series. And also the observable plays a major role. So if the observable is able to hone in onto the part where where we have the non-smoothness in the measure, then it's easier to detect. So we've developed a sensitive statistical test to detect this breakdown, and I'm going to give you some details on the coordinates a bit later. Okay, so back to linear response series. So what is known analytically, it all started in the 60s in statistical mechanics, so thermostatic Hamiltonians. Then it is known that for stochastic dynamical systems, linear response is valid. There's some recent work by Martin Heirer and Andy Meider. And then started to look at what about non-equilibrium dynamical systems, deterministic dynamical systems. So where you have singular measures, and then some seminal papers by Roel showed that for axiom A systems, linear response is valid. So then people had their hopes up, okay, we can show it for all other kinds of dynamical systems, but then Viviane Baladi and co-workers in a suite of papers showed that for logistic map and other unimodal maps, linear response is not valid. So what's happening there is the following. So I've shown here the invariant measure in the two colors of the logistic map. The two colors represent the measure for two very small changes of the logistic map parameters. So one is for, I don't know, 3.8, the other one's for 3.8.01. And you can see that the big peaks here, they vary relatively smoothly. They just are displaced a little bit. You can hardly see the difference here between those two large peaks. But they're the smaller peaks, and they have this, they jump if you change they're very fast upon changing epsilon. And then what you see here is, again, the average behavior. You see this non-smooth dependency on epsilon. And I want to stress this has nothing to do with periodic windows. So even if you restrict to the Cantor set of just the chaotic values and have some Whitney differentiability between those, linear response does not hold. So the current belief is that the sufficient condition for linear response is that the correlation function is summable. It's only sufficient. There's some very nice work of Alexei Korepanov that shows for intermittent maps that have non-summable correlation functions, we have linear response. And also it's known that it got nothing to do with structural stability. So that's not the defining factor that makes or breaks linear response. Okay, so now here again, the conundrum, how can typical observables of high dimensional systems, which consist of lots of low-dimensional systems, obey linear response. So we're gonna construct now a toy model scenario and then try to find conditions under which linear response goes. So we start with an uncoupled system. We're interested in some macroscopic observable. So phi is an average over some phi here observable that we require to be Hölder. So it's a macroscopic observable. It's going to be observed. And we have here microscopic systems that evolve to some microscopic dynamics. Notice they're all uncoupled. So each of those dynamical systems evolves independent of the others. But these different colors, they encode that the parameters of this map here, of this microscopic map, are chosen from some distribution U. And we're also gonna then look at a mean field coupled system, so where the microscopic dynamics feels the effect of the mean field. Okay, so these are these two scenarios that we're gonna look at. And here is the result. So we have here the macroscopic observer, if you're in the uncoupled or in the coupled case, and we're gonna look at two cases for the microscopic dynamic. It either satisfies linear response or it violates linear response. And if it violates, we want to look at that the parameters are chosen from a smooth distribution or from a non-smooth distribution. And we will see that there are differences between the finite case of a finite heat bath, we call it, or in the thermodynamic limit when we have infinitely many microscopic subunits. I want to draw your attention to the following. So we have now that what we're going to show is that microscopic dynamics can violate linear response, but the macroscopic observables have linear response. Here, if it's coupled, we're going to see that actually depends on the macroscopic dynamics of the macroscopic observable. So it could either be depending on the dynamics, it can satisfy linear response or violate it. And another interesting bit that I'm going to highlight, what we found is that even that you can have situations in the mean.
Cecilia, can you hear Georg? Georg, we can't hear you. I think you muted yourself somehow.
Better now?
Yes.
I got some sign that the host unmuted me, but since I'm the host, I might have done that myself somehow. Yeah, of course. Sorry about that. I want to draw also your attention to the following situation where actually all the microscopic units satisfy linear response, but the mean field couple, in the mean field coupled case, the macroscopic observable doesn't. Okay, so let's start in the uncoupled. Let's go step by step. Uncoupled microscopic subsystems. Given here, we look at these are just two examples of a smooth raised cosine distribution and just a combination of delta peaks where we draw from a finite set of the parameters. And we assume that each subsystem evolves independently and has a physical measure that is mixing. Then there are two expectation values. There's the expectation value with respect to the dynamics, so overall the initial condition. That's the one that's relevant for linear response. But there's also the expectation value according to the parameters that we denote with angular brackets. And so let's say all the microscopic subsystem satisfies linear response. That's the easy one. So we just need, this is our the object of interest. We need to look at the variation with respect to the parameter. And since all those subsystems here are satisfy linear response, we get linear response trivially. Same in the thermodynamic limit. It just follows straight through from the linear response of the microscopic subsystem. So that's an easy case. What about if they're not appropriately, if they do not satisfy linear response and they're not heterogeneous? So some of delta peaks here, then we can do the same spiel again And since now the measure here of E for each of the parameters, or here these measures are now non-smooth, again, linear response theory fails. So there's no linear response theory for the macroscopic observables in this case. So the question we're addressing now is, what about if we take smooth distributions? So if we have a smooth distribution here, then does the smoothing somehow lead to a linear response? So let's take, just to illustrate this, a very simple example. In the paper we go further. Let's imagine we apply a homogeneous perturbation to all the parameters. So for each particle j, the parameter is just added on an epsilon. Then we can look at this, the change of the observable here, make a change of variables, and then you see that the smoothness here depends on the the existence of linear response depends on the smoothness of our measure nu, that from which we draw the distribution nu, from which we draw our parameters. So if it's in BV, it's fine, and we can, if d nu dA is in BV, it's fine. So it works, and the degree of the smoothness tells you how many derivatives you can take here. So that tells you the degree of the response. So for the logistic map, you can make that more rigorous. And here's, I want to show you though, how this averaging of a smooth distribution leads to a linear response. I want to show you this graph here. So in black is the behavior in the thermodynamic limit of the response of our observable here. So that's smooth with respect to epsilon, whereas all the colored ones, they are for the individual dynamics. So this is just for particular J. So individual ones do not satisfy a linear response, but if you add them all up, then the averaging smoothes. Okay, so this again, we've just sent linear response to macroscopic observables. Now let's look at the finite heat bars. So now we can express this expectation value here. We can expand it around its thermodynamic mean, and we have a correction here. So this correction is a Gaussian process with respect to the perturbation epsilon. And now we see a problem because the differentiability of this epsilon here is of the same order as the differentiability here of our of the average of our observable, the one that we're interested in. But we've just shown that this one here obeys linear response, and this term here is small compared to this one. So we call this approximate linear response. So that means for us it's linear response for all practical purposes. So that term here, although it's non-differentiable, is dwarfed by the response term in here. So here you see an example where you see that you kind of have these sort of small variations. So for 3000, you can hardly see them around the smooth curve of the thermodynamic limit. So that we call approximate linear response. So so far we have explored the uncoupled case. So we have done this one. This here denotes the approximate linear response. Okay, so what about the mean field coupled case? So the strategy is now to derive a reduced equation for the mean field and then study the response property of this reduced equation. Note that now we have a time-dependent measure here because of the backcoupling of the mean field. And we will distinguish two types of mean field dynamics. If the mean field approaches a stable stationary state, or if it's chaotic, and we're going to see two different behaviors. Okay, so let's again do our linear response term, but now we have to look at conditional expectation values because they're now conditional on the history of the mean field, since we feed the mean field back in. So we have these conditional expectation values that we denote here by D for driver. And again, we can do the same spiel of expanding around the thermodynamic limit and look at the fluctuations, which again are Gaussian process in epsilon, but now with the additional conditioning on the history of the driver. And we can now use, we can now look at the driver here expectation value, or look at expand our observable around this one, and so this is now the central limit theorem of our dynamical system, and there we have the fluctuations are given by a Gaussian process with the following covariance. Note that because this is a non-stationary situation here, this is not a function of k here, right? This is not a function of k. Okay, so now we can write this all together. So the phi n is our thermodynamic limit plus those two terms, those two noisy terms that come from the respective central limit theorem of those two averages that we apply here. So the first one, that if we have mixing dynamics, we can just write as an f of f as a function of all those mean field terms. We can truncate if the decay is strong enough. We can truncate at some k. This noise term here, that's the bad guy, but it's typically smaller than the dynamical noise. We can control it. This dynamic noise, well, that's a good one. That's a dynamic self-generated noise. So in this system here for phi n, we can now write as this non-Markovian stochastic dynamical system. And in the finite case, we already have now immediately linear response given grace to this self-generated dynamical noise by just employing the theory of higher and minor. So this is a stochastic system that smoothes out all eventual complications that you could get from linear response to any potential non-smoothness. So the finite case is fantastic. That's done. That's good. We've done that. So for finite M, independent of the dynamics of the macroscopic variable, that one works. And here is an example. So 1000 is the kind of this finite case. It's over all this range of epsilon. It's smooth. You see, it's a smooth response. The thermodynamic limit is smooth here, and then it stops existing. And if we look at well, the curve here stops, and if we look at approximations of the thermodynamic limit, we see here it's nice and smooth, and here it sort of starts playing up. And what's happening here is a saddle node bifurcation of the macroscopic dynamics, and here a new state arises that is not stationary anymore. So this is a stationary bit that we just discussed, that we're going to discuss. And here, this is a non-stationary dynamics. But the finite, the blue curve, the finite heat bus case is smooth all the way through. So let's look at the thermodynamic limit. So we get rid of the bad guy here, but we also get rid of the good guy. So now our first example is trivial dynamics, where we converge to fixed point. And this is smooth if the uncoupled system has linear response. And this is this exactly this region in here where we have smooth linear response. Okay. So the linear response is inherited from the uncoupled case here for the trivial dynamics. Now here it appears the phi has non-trivial dynamics. So what's going on here? That's the non-trivial dynamics, and they're all invisible. So if the non-trivial dynamics is of the mean field is well, if it's non-trivial, it's not a stationary point, then lots of things are possible. In particular, the following. So this is interesting. Imagine all those subunits here, they're uniformly expanding maps. So the best you can get, linear response is valid. But now here is an example where the macroscopic dynamics is chaotic. And what you see here is now the response. So the response here in the thermodynamic limit is rough. Okay, so there's no linear response. So although the microscopic subunits satisfy linear response, the macroscopic response is non-existent. And so that finishes the discussion on linear response here. And on all those scenarios, we have now done the coupled one. So these are these cases where we can't decide, where it depends on the type of dynamics of the mean field. And I want to finish with a brief summary and also have the references down here, where this is all described in more detail. So we looked at the conundrum of how we can have a macroscopic response if the microscopic units do not have linear response. And what we used, the ingredients that we used were statistical limit laws. So we needed the observables to be holder, we needed the perturbed system to be mixing in order to justify those statistical limit laws. And we also showed the importance of having a heterogeneous heat bars so that we draw the parameters from a broad smooth distribution. And I want to highlight three cases. So the first one is we can have macroscopic linear response even when the macroscopic subsystems violate linear response. In finite mean field coupled systems, we have this emergent self-generated noise through the statistical limit law, and that ensures us linear response independent of the microscopic linear response. And then we have, this was the last case, we can have the violation of linear response for the macroscopic systems, even when the microscopic systems satisfy linear response. So it's everything is possible here, but it depends on the situation. So thanks very much.
Thank you, Georg.